Logarithms. This video is going to be the introduction to logarithms. I'll try to explain to you why we need them. They are pretty important because they're related to the exponential function that we just learned about. Okay, it turns out that the logarithm is the inverse of the exponential form. So, as we just saw in the last video, the exponential form is y is equal to a to the x, where a is just a number, it's greater than 0, not equal to 1, and that's the base, okay? So y is equal to some base value to the x power, and that's what we're going to call the exponential form, okay? As we saw at the end of that video, if you have y equals a to the x and that represents, let's say, some amount of money that you're getting on a compound interest investment, sometimes you might wonder not only how much is my investment worth after a given amount of years, but how many years will it take me in order to reach a certain value that I'm trying to get, some goal value. So let's say I want to make $10,000, and that's equal to this equation over here. That's the time right there. How long does it take until I can get that amount of money? I didn't show you how to do that. How would you be able to solve for x inside of this equation? The way that you're going to solve for x is by taking the inverse of the exponential. Okay, so the inverse kind of erases this a part and it tells you that x equals some answer. And I'll show you how it is. How to solve for x in this equation is that x is going to equal log base a of y. Okay, so this is actually the same equation. I didn't do anything except change the form. This is called the exponential form, and this is going to be called the logarithmic form. Logarithmic form. Okay, and this is what allows us to solve it for x. This one is solved for x, and then this one is solved for y. And these are basically the same exact equation in two different forms. Okay, so if we want to understand how long it will take for the investment to reach a certain amount of money, we would have to solve for x by taking the logarithm base a of the value y. Okay, maybe it will explain it a little better if I show you a picture of this. So let's look at the graph of the logarithmic function here. Okay, and now in green, I'll draw the function y equals a to the x. So let's assume that we're working with a base a, which is greater than 1. And I'll tell you that usually your base a is not only not equal to 1, but it's going to be greater than 1. The most common format is that we use a base that's greater than 1. Here, that will be represented by exponential growth, and the logarithm is the inverse of that. And so that looks like this. This is the function, let's call it y equals log base a of x. So now, what does it mean for these two things to be inverses of each other? Basically, when I solved it for x in terms of y, you see how I said that this was the same as this equation right here? X equals log base a of y. But over there, I wrote it as y equals log base a of x, because usually this is the y-axis and this is the x-axis. But you can see the blue compared to the black. What I did was I switched the x and the y. I switched the x and the y. So what does that mean visually? This is the x, this is the y. Let's pretend that we have a line that we've drawn right here, this horizontal line. This is the line y equals x. What happens if I switch the x and the y? What if I wanted the x to become the y and the y to become the x? That would be like taking this green line and pretending that this is a piece of paper that we're going to fold over this dotted line. Okay, so if I could just rip this right off and then fold it over the dotted line, what would happen is the green line would get pasted onto this blue line. That's what it means to be the inverse of that function. Okay, is that if you switch the x and the y's, the green function becomes the blue function, and that's what allows us to take this and write it in a form where it's solved for x. Because before it was solved for y, and now it's solved for x. Okay, so what I want you to take away from that is just a few things about the graph. For instance, do you guys remember what point is on this green graph? No matter what the base a is, what point does it always go through? That's right, it always goes through the point x equals 0, y equals 1. right? It always goes through that point. So one thing that you really want to remember when you're trying to think about and visualize what a logarithmic function looks like here is that I switched the x and the y. So that means the log function always goes through the point 1 comma 0. That's what it says. So if it always goes through the point 1 comma 0, that means that the log base a of 1 is always equal to 0. Because I will plug in that value for x and I will get that value for y. The log base a of 1 is always equal to 0. This is something that students often forget, but hopefully you can remember it by using this visual tool, and also remember it from the fact that this is the equivalent statement of saying that the base a to the 0th power is always equal to 1. And that's something that people usually remember a little bit easier. If I do 3 to the 0, 4 to the 0, no matter what number I put to the 0, I get 1. And so no matter what base I'm logging in, if I'm taking the log of the number 1, I get 0. Okay? The logarithm is the inverse of the exponential function. And one thing that you can think about to help you understand logarithms is that the logarithm is in fact an exponent. The logarithm itself is an exponent. Okay, so I'm going to write that underneath here. The logarithm is the exponent, the value of the exponent x that obeys the statement that y is equal to a to the x. Okay? So you can think about this logarithm function taking an input, just like all functions take an input and then they give an output. When you put something into the logarithm function, it is the thing that was coming out of the exponential function because the input and the output got switched. Okay? So when I throw something into the logarithm, what gets spit out the other side? What is the output of the logarithm is the exponent. It's the exponent that came from this exponential equation. So it's the value of the x that was up here in the exponent. Okay, so let's see that in action with a couple statements now, aside from the graph. Okay, so let's just do some examples, and I'm going to start with the base that most people are the most familiar with, which is base 10. Base 10, because we have 10 fingers, so I think naturally people started counting into base 10. So for example, let's say we define an exponential function, y equals 10 to the x. So the base is 10, and this is the exponential form, okay? This is the exponential form right here. Now let's make a couple statements that we can understand are true, and then we're going to see the logarithmic equivalent form of that. Okay, for example, if I take 10 and raise it to the 3, I get 1,000. If I take 10 and raise it to a 6, that's 1,000,000. Right? That seems like it makes natural sense to us. That's the exponential form. Okay, and now let's see that equivalently inside the logarithmic form over here, keeping in mind that when we take a logarithm, first of all, the base that we take it in should correspond to the base that we were working in when we were doing an exponential form. Okay, so if I want to do the equivalent logarithmic form here, I'm going to use log base 10. You see the little a down there? You have to say log base 10. Okay, and now remember that what you put into the log is what you got out of the exponential form, okay? So the y that was coming out of the exponential now becomes the input for the logarithm, and the thing that gets spit out of the logarithm is the thing that was the exponent. That's what I mean by the log is the exponent, okay? So if I ask you what's the log base 10 of 1,000, the answer is, what is the exponent that I would raise 10 to that thing so that I would get 1,000? And the answer is, well, 10 to the 3 is 1,000. So the log base 10 of 1,000 is 3 because 10 to the 3 is 1,000. The output of the logarithmic function is an exponent. It was the exponent that we were using over here. Okay, so why don't you try to take that example and write down here the equivalent logarithmic form of this exponential statement that 10 to the 6 is 1,000,000. Okay, so let's see if you wrote it down. What I'm looking for here is that the log base 10 of the number 1 million, that's going to be the number that I would raise 10 to in order to get a million. And the answer is 6. Okay, exponential form, logarithmic form. Boy, I got a lot of these, so we're going to go back to this table where we compare exponential and logarithmic forms. But one more quick lesson, and that's just a little bit of a general lesson on inverses. What does it mean to be an inverse? And you'll mainly just be using this for this pair of inverses, exponential and logarithm. Okay, so f of x and g of x, two functions, are inverses of each other. Now, do you guys remember all the way back when we were studying what a composition of functions is? This goes back to the composition of two functions. If I take f and then I put g inside of f and I get out the thing I started with, x, that's an inverse. Those two things are inverses. And if I take g and I put f inside of that and then I get out the x that I started with, then those are inverses of each other, okay? So let's just think about this for a minute. X is the original input, right? So if I take x and I put it into g, and then I take the output from that and I put it into f, and then I get back where I started, that's an inverse, okay? Let's think about it this way. We start with an x and we go over to a y, right? And then if we take x and put it in f and it goes over to y, but then we take that and we put it in g, and we get back to x like this, then we would get back where we started. That's why it's called inverses, because you go over somewhere and then you go back to where you started. Okay? And inverses are very powerful because they allow us to solve for x. For example, if I'm up here and I want to know, let's say my output is like 500,000, what's the exponent on a 10, where 10 to that thing is 500,000? I don't know, and it's not going to be an easy thing for me to guess either, because it's not going to be a whole number, like if I had a million for my output. So the only answer, the best bet for me in order to be able to solve for x, is to say that, well, x is going to be equal to the log base 10 of y. So I'm going to put the y into a log base 10 using my calculator, and whatever number I get out x is the exponent that's going to make that work. Okay, so this is all true right here, but really I want to do it for the special, very special two functions of interest here, as e to the x and, let me start with the arbitrary base a and then I'll explain the e to the x thing. Okay, so a to the x and log base a of x are inverses. Yay, it's a pair, a to the x and log base a x. Okay, and when I had started to write, I already just naturally wrote it down because it is the natural base, is e to the x. Do you guys know what the e stands for? E actually stands for a mathematician back in the day, Leonard Euler, spelled E-U-L-E-R, and this is Euler's constant. He's one of my favorite of all-time mathematicians. This guy's really cool if you want to look him up on Wikipedia. And the E is approximately equal to 2.71828 ... It goes on forever, kind of like how pi is equal to 3.1415 ... This is a transcendental number, so it doesn't really have a finite decimal equivalent, but it is also known as the natural number. We're actually going to see how the natural number is derived in the context of mathematical finance later when we get to chapter 6 and we talk about compound interest. So that'll be fun, but for now, just take my word for it that the word natural is truly referring to nature, because this is how nature grows. This has been observed in biology, physics, chemistry, all over the place. You're going to see the base E pop up because it actually is the natural way that things form at the very base level of life. Okay, so e to the x is what we call the exponential form with the natural base e, and its inverse is going to be log base e of x. But we actually don't call it. See how I replace the a with the e here? I replace the a with the e right here. we don't call it log base e of x, we call it ln of x. Okay, so just so you know, if you see ln instead of log, the normal log, the ln doesn't come with any subscript there because it represents the log base e. We call it ln of x, and that's the natural logarithm. Okay, so this is the e to the x, and in its inverse is ln of x, the natural logarithm. Okay, these two things are inverses of each other, which, remember what I was saying before, says that if I compose the two functions together, I'll get right back where I started with. Okay, so let's define f of x as e to the x, and let's define g of x as ln of x. Okay, so f of g of x is actually e to the ln of x. And if you ever see a statement where I've taken the base e and I've exponentiated it to the ln of x, that's just x. That's because they're inverses of each other. And likewise, the other fact was that if I compose them in the other manner, with g as the outside function and f as the inside function, that would be the statement that the outside function being ln of x is ln, and then the input, the inside function, e to the x. Once again, the thing that I'm going to get out here is x. Okay? So e to the ln of x is x, and ln of e to the x is x, and that's actually true in all bases. So like, for example, let's work in base 10 because this is something that people are pretty familiar with. What I'm saying here is that if I compose the function 10 to the x, and I take as the exponent, I take log base 10 of x, I'm going to get x. That's right. You see, whenever the 10 is exponentiated to the log, then you just get the x back again. And likewise, if you take the log base 10 and you put as its input 10 to the x, you're going to get out, you guessed it, x. Just the x that you started with. That's because they're inverses of each other. And so this is true in base 10, it's true in base e, and it's true for all bases, which is to say that base a raised to the log base a of x is equal to x, and the log base a of the quantity a to the x is also x. Okay, it's true in all the bases, and why, again, do you care about this? Is because a lot of the equations in mathematical finance are going to heavily involve exponential type of functions. And if you want to solve for like how long it's going to take you to get to some goal amount of money or do other various calculations, you will need to solve for the exponent, and that's where the logs come in handy. Okay, so this is really important for the stuff that we're going to learn in the mathematics of finance. So just bear with me as we go through another chart of the exponential form versus the logarithmic form. Okay? So in these two columns, I'm going to write down some statements, and I'm going to want you to consider what the equivalent or same statement would be in the other form. Okay, so we just saw an example of that before. The example before was that 10 to the 3 is 1,000. Okay, so without rewinding or looking at your notes, what was the logarithmic form of this statement? Yeah, that was that the log base 10 of the number 1,000 is equal to 3. The exponent 3 is the thing that makes that happen. Okay, so let's look at some other forms. Like, for example, if I said that y was equal to e to the x, another one that we kind of were just going over, what is the equivalent statement of this in logarithmic form? Yes, it's that ln of y is equal to x. You see, the output has now become the input, and the input has now become the output because they're inverses of each other and the x and y got flipped. Okay? Let's practice some more concrete examples. For example, 10 to the minus 2 equals. Okay, so just to review from the last video, what does 10 to the minus 2 equal as a decimal? It's 1 over 100, 1 over 10 to the 2, so 0.01. Right, okay? So what is that equivalent statement in logarithmic form? And you might want to use this line to help you when you try to figure out this line. Because we're still in base 10, right? So what I'm looking for here is the logarithm base 10. And now what's going into the logarithm is the output that was coming out before. So 0.01, and that's going to be -2. You see how the answer, the output to the log, is the base? I'm sorry. The output of the log is the exponent, okay? So the output of the log is the exponent. As if it weren't confusing enough, sorry. Okay, let's try some more. You're going to need a lot of practice in this. So you might want to just go outside of your text and kind of search for exponential versus logarithmic form on the internet, and you can see many more examples of stuff like this. But let's just throw some more up there right now. Okay, so now maybe I'll start with the logarithmic form, and then you try to put it in the exponential form. Okay, so what if I said that log base 3 of 9 was equal to 2? What is that supposed to mean? Is that just gibberish to you? I hope not. I hope you're really trying to think about what it means to take a logarithm. Okay, so log base 3 of 9 is 2. What is that trying to say to me? In the exponential form, it becomes clear that what I'm saying is, if you take the base 3 and you raise it to the exponent 2, then the output you will get is 9. You see that? Does that make sense? Okay, so let me do some more. What about the log base 3 of 81 equals 4? Okay? Or what about the log base 7 of 1 is equal to 0? Okay? Actually, let me give you a couple more. How about, or one more, the log base 2 of 16 is equal to 4. So take all these logarithmic forms and now write them as exponential forms. I think they'll make more sense in exponential form. And I gave you some that maybe just will look familiar to you as well to help. Okay, so when you start to translate it backwards, keep in mind that what you want to start with is you look for the little subscripts, because that's the base. Okay, so we're still in base 3 on the second line, and then you take this and you put it in the exponent, 4, and then the input from the log becomes the output for the exponential form. Okay, and 3 to the 4 is 81, so that makes sense. Alright, what did you get for this one? What is it saying? That's right, 7 to the 0 is equal to 1. What about 3 to the 0? That's 1 too. What about 5 to the 0? That's 1 too. Anything to the 0 is 1. In fact, so this brings up another point, which is that any number to the 0 is 1. Okay, so since I already know the fact that any number to the 0 is 1, no matter what the base is, if I raise it to the 0 I get 1, then I also have that the log base A of 1 is equal to 0. That's the equivalent statement in logarithm land, is that no matter what your base is, if you had raised it to the 0, your output was 1. So if you log a 1, you always get 0. Oh yeah, remember the picture? That's a picture of the logarithm. Remember that? And it always goes through this point right here, 1, 0, whereas the exponential always went through 0, 1. Okay, I hope this is making as much sense to you as it is to me right now. Let's go to this last one. What is the exponential equivalent of that statement that the log base 2 of 16 is equal to 4? 2 to the 4 is equal to 16. Nice. That's the statement. Okay, so let's try a couple more and then we'll call it a day on this. Let's try to do writing things in the different requested forms. Here's a couple. How about try writing this in logarithmic form? And how about try to write this in logarithmic form? Okay, go for it. Alright, so hopefully you recognize that when you are writing down the logarithmic form, you have to pay attention to what base the exponential form was in. So this one's in base 5 here, and so that starts me off with an answer that I'm doing a log base 5. Okay, and then what was coming out, the 125, now goes into the log, and the answer that pops out is the exponent that was put in, okay? 5 to the 3 is 125, so log base 5 of 125 is 3. Okay, oh, this one's kind of weird as a negative number. Where's that negative number going to end up, I wonder? Okay, so we're going to start this out by saying the log base 10 because we had to the 10 over here. And then we have to put 0, 0, 1 in here, and the output is negative 3. Okay, let's talk a little bit about the domains of both of these functions. So I'm going to go back to the graphs for a minute so you are aware of what types of things you can put into each function and what type of things that you get out of each function. So here's the exponential versus the logarithm. And we'll go to their domains and ranges. Okay, so this is the exponential, y equals a to the x, and this is a logarithm, which says y is equal to log base a of x. You guys remember what domains and ranges were? Domains is the kind of things you can put in, and range is the kind of things that you can get out. Okay, so let's see. For the domain of an a to the x type of function, what kind of numbers can I put in? What kind of numbers are okay to put for x? Positive numbers okay? 0 okay? Negative numbers? Oh, you can put negative numbers in there too. Sure, you can do 3 to the minus 2, 10 to the minus 3, whatever. The domain for here is x is in R. So that's all the reals. Okay, you can put anything you want in there. Now let's talk about the range. What kind of things pop out of the exponential function? Can you get a positive number out? Yeah, it looks like all these numbers are positive. Can you get a negative number out? Actually, no. I can't see any single place where if I take a number for x and put it into the function, that I would get a negative y. I get no negative y's out of here at all. And that tells me that, like, if I was in base 10, if I raise it to a positive power, I get a big number. If I raise it to a negative number, I get a little number. But I never, ever get a negative number out. There's no exponent I can raise 10 to and get like negative 6 out of it. Okay? So the range here is that x has to be greater than 0 and it goes on to infinity. So I'll just write that, as y is greater than 0. So only positives numbers come out. Okay? Only positive numbers come out of the exponential form. Alright, now let's go over here to logarithmic land, and we'll see what's the domain on a logarithm here. And keep in mind, those are the numbers that are okay to put into a logarithm. And since the numbers that we put into the logarithm are the same numbers that were coming out of the exponent, and according to the picture, what do you think the domain is here? X has to be greater than 0. Only positives. Yeah, you see how this graph is only graphed on this side of the x line? There's no part of the graph. Go ahead and try it yourself on your graphing calculator. If you graph a logarithmic function like the ln or the log base 10, there's nothing over here. Because you can't put negative numbers in it. You can only put positive numbers in. So this says that only positive numbers go in. How come I can only put positive numbers in, huh? Oh, yeah, that's because only positive numbers were coming out of its inverse, the exponential function. You see, is it making more sense now with the switching of the x and the y? Right? And so likewise, since the domain of this is all reals, that becomes the range in the other function here, is that all real numbers come out. So y in R is the range of the logarithmic function because can I get positive y's? Sure. Can I get negative output from a logarithm? Oh, sure. Yeah, look. I just got a negative output right here. I just got that the logarithm of 0.001 is negative 3. In fact, you're always going to get a negative y out if you put in a number that was less than 1. You notice how this number right here that I put in was less than 1? That's the theme. Because when you get a negative exponent, that's like 1 over the number. Okay? So that's why you're getting negatives out, but you can never ever put a negative inside a logarithm. Okay? So don't try to take the log base 10 of negative 2. Error, error, because I could have never got the number negative 2 out of this. Okay, good. Let's just go into a couple examples of solving equations, and then that'll be it for your introduction to logarithms. Okay, so let's say, for example, I want to solve for x. And I have the statement that the log base 7 of 2x plus 19 is equal to 2. Yowza! Where did this equation come from? Well, it can happen, okay? Just trust me that, as you move along into the next chapter and such, you might start to see equations like this pop up. And how are you going to solve this thing? You probably want to rewrite it first into its exponential form, and then you can solve it out. Okay, so this is more practice in switching from logarithmic to exponential form, vice versa. Write this in the exponential form, the equivalent exponential form. You got it? Now, how are you starting it out? You're starting it out with a base of 7, because it's log base 7, okay? So base of 7. And then this is saying to me that 7 to the 2, remember, because the output of a logarithm is an exponent there, 7 to the 2 ends up being this right here, 2x plus 19. Okay, so when you see it in the exponential form, do you see how much easier it's going to be to solve now? Because 7 squared is 49, so really I'm just telling you that 49 is 2x plus 19, and that's a linear equation. I'm not even going to go through the hoopla of solving that, but hopefully you can solve that one out to get to the answer that x equals 15. Okay, this is just a simple linear equation. Subtract 19 from both sides, divide by 2, then you get x equals 15. Let's try that one more time. What if I told you that the log base 4 of x minus 5 was equal to 3, for example? What's the x? I don't know. I can't solve it like this. I have to write it first in its exponential form. Then I'll be able to make more sense of it. Okay, so the exponential form is in base 4, right? And I'm raising that to the 3. And the output I'm getting is x minus 5. That makes a lot more sense because I know that 4 to the 3, that's 64. And then that's x minus 5, so then adding 5 to that, x is 69. Alright, that was pretty easy, right? The hardest part of that was going from here to here. So that's why we studied that so much. And I'll just give you a couple more to quiz you and make sure that you really understand the logs. What's the log base 7 of 49? Don't use a calculator. Think about what I'm asking and what that means. What's the log base 3 of 1 over 27? What's the natural log of e to the 12? And what's e to the natural log of 4? This is it, I promise, for this video. Fill out this chart by thinking about what they mean. Okay, so let's talk about it. This top one, log base 7 of 49, means what's the exponent that I would raise a 7 to get 49? Well, I know that 7 squared is 49, so the exponent must be 2. What's the exponent that I would raise a 3 to get the number 1 over 27? That's a fraction. So I'm guessing it's going to be a negative exponent, right? Notice how the input to this log is something that's less than 1. So from the graph now, I'm expecting a negative number out. And what's that negative number? Negative 3. And that's because 3 to the negative 3 is 1 over 27. See, this one was because 7 to the 2 is 49. Okay, so let's do a couple more. What's the ln of e to the 12? Now maybe you wanted to just keep in mind the ln of e, just like every other base and its corresponding logarithm, are inverses of each other. So if I compose these two functions together, I'm just going to get the exponent back. Really, the thing that I'm saying here is, what is the number that I would raise e to in order to get e to the 12? Well, that's a silly question. You would raise it to the 12, wouldn't you? So that's why log e to the 12 is 12, and if you like, you can just see that as a composition of functions. Bam, cancels out. You get 12. Okay, so try that on this one. Think about it in terms of a composition of functions. Again, I'm composing the e to the log. And bam, they cancel out, and I get 4, exactly. So that's why it's 4, because I'm raising e to the value of an exponent such that I would get 4 out. So of course I get 4 out. Okay, it's a little confusing if you think about that one. So you might as well just keep in mind that e to the log cancels out. Log to the e cancels out. And that's the same whether I'm in base 10, 3, 5, any base at all. But especially want to think about log base e, the natural log.